So what did we get from that? We have now some idea that the time dependence of the dielectric response relates to this refractive index change, this dispersion that we've seen before. That's one good thing. But what we really need for going forward now in the shape of light is the plane wave, because we are going to learn a lot about light and how it propagates just from the plane wave. And the plane wave is the solution to the wave equation, so we need to derive from Maxwell's equations the wave equation. This is a derivation that any electrical engineering student that works with light should probably be able to do on the back of a napkin. It's a really simple thing, it connects what you're doing to Maxwell's equations. So the steps are, we take Faraday's law, which related E to the time derivative of B, and we take the curl of both sides. And we do that because the curl of B, of course, is Ampere's law, the curl H. We substitute in for B, mu naught H, and it's only mu naught because the relative permeability of materials at optical frequencies is almost always 1. And then we use Ampere's law to substitute from del cross H into D. And finally, the other constitutive relationship from D into epsilon naught epsilon E. And I've written it down here in the fully anisotropic case, but if you don't like that, just get rid of all the vector and tensor signs. So the point is we use both curl equations and both constitutive relations. So we have pretty much used all of Maxwell's equations because the divergence versions of Maxwell's equations are, if you remember, included in the curl equations. So now we've eliminated the magnetic field is the point. We had two first order equations relating E to B and D to H, and now we have a single second derivatives right here, equation relating E to E. Now we're going to go monochromatic. We already have monochromatic. So we just rearrange this equation, and just like we used the resonant frequency of the dipole earlier on, we're going to recognize that some of these terms here are the vacuum wave number, 2 pi over the free space wavelength. This is the vector wave equation with its anisotropic term right there. Monochromatic, there are no time derivatives, so this is in the frequency domain. And most of the time, we'll just worry about scalar waves here. So we'll get rid of this tensor. We'll call these vector electric fields just scalars. We use a vector identity on curl, and we get to the scalar simplification. And if you take del squared here, this is just in all 3 dimensions, the second spatial derivative. So the simplest version of this is the second derivative of the electric field, let's say with respect to Z, is k squared E. So that's your classic simple wave equation. That's the equation we're solving in this whole course. And the whole point of the last few lectures is simply you should know how that came from Maxwell's equations and what approximations or not went into it.